Hello everyone, my name is Grima. This is my presentation of physical chemistry with the topic Hittorf's method. So, Hittorf's method, its principle is that this method is based upon the principle that the fall in concentration around an electrode is proportional to the speed of the ion moving away from it. Example: fall in concentration around anode upon divided by fall in concentration around cathode is equal to speed of anion divided by speed of cation. And on adding 1 to both sides, we will get 1 plus fall in concentration around cathode upon fall in concentration around anode gives speed of anion divided by speed of cation plus 1. On equating all this equation, we will get that speed of cation divided by speed of anion plus speed of cation gives number of gram equivalents. So if the concentration are expressed in terms of gram equivalents, then NC is equal to number of gram equivalent lost from the anodic compartment divided by number of gram equivalents lost from both the compartments. So the number of gram equivalents lost from both the compartments is equal to the number of gram equivalents discharged on each electrode. Thus, in turn, can be found by placing a silver or copper voltmeter in series as according to Faraday's second law. When the same quantity of electricity flows through the silver or copper voltmeter, the same number of gram equivalents of Ag or copper will be deposited. Thus, the above formula reduces to Nc is equal to number of gram equivalents lost from the anodic compartment divided by number of gram equivalents deposited in voltmeter. Thus, the determination of the transport number of the cation involves the determination of the number of gram equivalents lost from the anodic compartment and the number of gram equivalents of silver or copper deposited in the voltmeter placed in series with the apertures. However, it is important to note that the above result is applicable only when the electrodes are not attacked by the ions. If the electrodes are attacked, the result is calculated in a different manner. To determine the transport number of anion, there is no need to find the loss in concentration of the cathodic compartment because a transport number of anion can be calculated directly from the equation transport number of anion is equal to 1 minus transport number of cation. So the apertures used for this is evidently the aperture should be such that it should consist of three compartments, namely the anodic compartment, the cathodic and the central compartment. The solution of these compartments should not mix with each other on electrolysis, and it should be possible to take out the solution of any compartments without disturbing the solution of other compartments. It consists of a U-tube joined on its two sides to two vertical barbed glass tubes. All the three, example the U-tube and the two vertical tubes, have got the stopcocks at their bottom. The U-tube is also provided with two stopcocks, one on either side at the top, so as to cut off the various compartments from each other when required. In the two vertical tubes are placed the anode and the cathode separately. These are of platinum. If it is desired that these should not be attacked by the ions, alternatively the anode and the cathode of silver or copper are taken depending upon whether transport number of silver ions or copper ions is to be determined. in which case the anode is attacked by the ions. The aperture is connected to a silver or copper voltmeter, also called coulometer, in series with the apertures together with a battery, a rheostat, a key, and a milliammeter. The apertures of this is like this. These are the three compartments. This is anodic compartment, cathodic compartment, and this is the central compartment. These are fitted with two stopcocks to stop their mixing. There is a rheostat, milliammeter, battery, and this is a voltmeter with two copper or silver voltmeters. The procedure for this is that first the aperture is filled with the solution of the electrolyte, the transport number of whose ions is to be determined. A silver or copper voltmeter is placed in series with the apertures and the various connections are made. Before electrolysis, the concentration of the electrolyte is found by titrating a known weight of the solution against a suitable reagent. Example against KSCN solution for AgNO3 solution and against hypo solution for CuSO4 solution after adding Ki into it, etc. Now, a current of 0.01 to 0.02 ampere is passed for 2 to 3 hours. A low current is used so that the change in concentration around the electrodes is not too high, as otherwise the diffusion may take place. After electrolysis, the solution from the anodic compartment is taken out, weighed, and then titrated as before to know the amount of the electrolyte present. The weight of the silver deposited in the silver voltmeter is also determined. The solution from the central compartment is also taken out and titrated to see that there is no change in concentration. In case a change in concentration is observed, the experiment is repeated. It is important to note that in these measurements, the weights of the solution are taken instead of volumes. This is necessary because after electrolysis, the density of the solution changes and so does the volume. Now we will do calculations. The method of calculation may be illustrated by taking the example of AgNO3 as the electrolyte and using silver voltmeter in series. So the case 1 is when the electrodes are not attacked. Example, when platinum electrodes are used. So after electrolysis, suppose weight of the anodic solution taken out is W1 gram. Weight of AgNO3 found to be present by titration is W2 gram. Therefore, weight of water present is W1 minus W2 gram. Thus, W1 minus W2 gram of water contain W2 gram of AgNO3 after electrolysis. In terms of gram equivalent, W2 gram of AgNO3 is equal to W2 divided by 170 gram equivalent of AgNO3 equal to W2 gram of by 170 gram equivalent of AgNO3. Hence, we can say that after electrolysis, W1 minus W2 G of water contain X gram equivalent of Ag. Now, before electrolysis, suppose W3 gram of solution contain W4 gram of AgNO3. Therefore, weight of water present W3 minus W4 gram. Thus, W3 minus W4 gram of water contain W4 gram of AgNO3 before electrolysis. Therefore, W1 minus W2 gram of water will contain gram of AgNO3, which on solving gives Y gram equivalent. Say. So W1 minus W2 2 of water will contain Y gram equivalent. When the electrodes are not attacked, means X is less than Y. Falling concentration of the anodic compartment is equal to Y minus X gram equivalent of Ag. Suppose the weight of silver deposited in the silver voltmeter is equal to G W gram is equal to W by 108 gram equivalent of Ag is equal to Z gram equivalent, say. Therefore, transport number of Ag positive ion is equal to fallen concentration around anode in gram equivalent divided by amount of Ag deposited in voltmeter in gram equivalent is equal to Y minus X divided by Z. So, transport number of NO3 negative ions is equal to 1 minus NH positive. So migration velocity of ions and change in concentration when electrodes are not attacked. In this there are four cases. First case is that when there are equal number of ions in cathodic and anodic compartment. Second case is that when two ion two negative ions migrate from cathodic compartment to anodic compartment. Third case is when two ions equal number of ions migrate from anodic compartment to cathodic compartment and cathodic compartment to anodic compartment. Fourth case is when one ion migrate from cathodic compartment and two positive ions migrate from anodic to cathodic compartment. So now we are going to discuss the second case. This one. So second case is when the electrodes are attacked, means silver electrodes are used. In this case, the NO3 negative ions reaching the anode attack the silver anode. There is increase in the concentration of Ag positive ions in the anodic solution instead of decrease. In this case, we will have X greater than Y. Therefore, increase in the concentration of the anodic solution, that is X minus Y gram equivalent of Ag. This increase in the concentration takes place in spite of the migration of Ag positive ions from the anodic compartment to the cathodic compartment. If no Ag positive ions had migrated from the anodic compartment, the increase in the concentration of Ag positive ions in the anodic compartment would have been higher and equal to Z gram equivalent of Ag. Example, the same is the amount deposited in the silver voltmeter. Hence, fallen concentration in the anodic solution due to migration of Ag positive ions is equal to Z minus of X minus Y gram equivalent of Ag. Transport number of Ag positive ions is equal to Z minus X minus Y divided by Z. So transport number of NO3 negative ions is equal to 1 minus N of Ag positive. Now this is the case when migration of velocity of ions and change in concentration when the electrodes are not attacked. So this is all about Hittorf's method. So thank you.